I wanted to talk to you this morning about what I've been working on, which is related to type theory, but in some sense a little different. I'm kind of glad that Guillaume went yesterday and talked about sort of a logical definition of weak infinity groupoids. Well, I'm going to sort of try to do something similar. I'm going to try to give sort of a language, an internal language for omega categories. So I'm going to allow, so one object of sort of what I've been working on is to allow for non-invertible things. And to do that, and second, there's sort of a more philosophical reason behind what I'm doing, which is to use a different set of shapes than any of the ones we've talked so far about. I guess we've talked a lot about higher categories defined in terms of presheaves on the simplicial category, which people call simplicial sets, and there's a nice approach to, well, Kohn complexes represent weak infinity groupoids here. Yesterday we talked about presheaves on the globular category, which are called globular sets. And this is also a very nice approach, and Guillaume showed us how to sort of treat these logically. And then there's another approach, which is, well, presheaves on O-op, so functors from this category O into set. And I'm going to sort of try to work with this approach. And so first, maybe the first task is to describe for you what this category O looks like, okay? Well, that's because they're presheaves on O-op, in other words, functors from O into set. So in this case, I'm going to describe O itself, and then they will be, yeah, so there's that weird op thing. Okay, right, so in contrast to these two categories, which have a very sort of simple combinatorial description, this one doesn't. This category is quite a bit more complicated. There's more objects already. I mean, you can think of these filtered by dimension, and in this category, there's one object of every dimension, the n-dimensional simplex. In this category, there's one object of every dimension, the n-dimensional disk, I guess you can think of it. But here, there's already going to be infinitely many objects in dimension 2, so it's quite a bit more complicated. Right, and so you can sort of draw pictures of the things in each dimension here. And then, right, how do people do this? And you could draw pictures here. Right, disk, ball. But of course, then we sort of, in these two categories, we sort of have to stop, right? Because, and change to some mathematical notation. Here, we don't need to describe the higher objects because this category is so symmetric that we can just write it down. And this one, we have this nice presentation in terms of linearly ordered sets. So here, we're going to be able to, I'm going to give you a definition of what the objects are pictorially, okay? So diagrammatically. I'm going to just show you how to represent any object in this category. And then I'll show you how to represent the maps. So the main idea, so let me first draw a couple examples. They're going to be pictures that look like this. So here's one example. And then maybe I'll do this. So, oh, I shouldn't get too fancy. Let me make the first one very simple. Okay, here's an example of one, okay? And I'm just going to show you what I'm doing, okay? It's very simple. This is one thing. This is, and you can label these by dimension. This is 0, 1, 2, 3. This is an element of dimension 3, okay? And right. And so I'll just show you what I'm doing. So to get one of these objects, you have to satisfy a couple of rules. So the first thing is it's going to start with a list of boxes, a sequence of nested boxes like this. Okay, so the first thing will always look like this, and it can go on as long as you like. Okay. Now, to proceed from here to here, the first thing I do. No, just some nesting of arbitrary depth. So I could keep putting boxes around this first one. I'll think of it as a linearly nested sequence of boxes of any depth. Okay. When I picture these, by the way, I picture this as like a stack of cards, and you're looking at the top. So this one's on top, this one's below it, and this one's below it. The first thing is a number. Okay. So to proceed to the next dimension, what I'm going to do is I'm going to draw a tree corresponding to the boxes I see in that dimension. Here, it's a linear tree. And so it's going to have, so if I start labeling these things, I'll label this X, Y, and Z. The labels on each box correspond to the lines in the next picture. Okay? And then I add, and these boxes are, so I'm thinking of this as a linear tree which looks like this, except for I'm drawing these two dots as open boxes right there. Okay? So now after you do that, what you do is you make a linear sequence of, you put boxes under the boxes that you've drawn. So here I put one around like this. And now what I do to proceed to the next dimension, oops, so I did this one wrong, didn't I? Yeah, sorry, this shouldn't have, my fault. This shouldn't have boxes like this. It should look like this. Is I draw the sequence of boxes corresponding to this. So if I write F, G, and H here, the tree in the next picture corresponds to how the boxes are nested within each other. So F, G, and H. Okay? And then you go to the next dimension, and you're allowed to put any number of boxes below this one right here, so that they form a tree when you look vertically. And then so here I could call this alpha and beta, right? And then so this one, now that I've fixed it, looks like this. Alpha and beta are here, and this I could call theta. Okay?
Next thing is on level 1, that you can rank boxes in new boxes and so on.
Yeah, you can just. What's that?
Can you do that also on the higher level?
Yeah, so you can make things sort of more complicated. Let's do another example. Okay, the first one has to be linearly nested. Now, I draw a tree, now that I've told you how to do it, corresponding to these three things right here. So always in every picture, the lines in one picture will draw exactly the tree corresponding to how the boxes are nested in the picture before. That's it, okay? So now I'm allowed to put boxes around these. So I could do something like this, do something like this. And I'm done. Well, I can. One requirement is that there be one box which contains all the other ones. This one looks like this. Okay. Now, so now I just am going to try and draw this tree. This edge corresponds to this one, which, right? The leaves, the outgoing things of the tree will correspond to the boxes for which the line does not cross the interior. Okay, does that make sense? So I'm going to consider these special boxes which live on the outside, which don't have the line crossing the interior. These boxes are special. And you can see the leaves of the tree correspond to those, and the internal edges of the tree correspond to the ones below them. Okay, so this one looks like this. Then it looks like this, like this, like this, like this. Okay, so then I get a tree like this. Yeah?
In dimension 0, why did you only color the X?
I colored exactly the boxes which are sort of external, on the top. They're not covered by anything else. I'm thinking of Y as like living below, Z is below, F and G are on the outside. And that'll be important later. Okay? So
You're drawing them on the outside, but you draw them on the inside.
sorry, yeah, but I think of looking them. I think of these things. I think that I'm looking from the top, and then they're on the external. Okay, and then so you could continue like this, and you could make this one as much more complicated as you want. But let me just stop here, and then this is going to have exactly 3 external leaves corresponding to, again, the 3 boxes on the outside. Does that make sense? So here, if I would box these. Okay, and those things are sort of external. Okay, now the point about these is, well, okay. Oh, I lost an eraser. Let me tell you. So these are the objects. Okay, the objects start with a linear sequence and end with a corolla. Okay, so they have to end with a single thing. Okay, the point about these things is they exactly correspond to, let me erase these things, they exactly correspond to a certain class of pasting diagrams. Okay, so what I'm going to do now is I'm going to turn this into geometry. Okay, so so in dimension 0, we have 3 points, x, y, and z. Okay, in dimension 1, we have 3 arrows, f, whose input is x and output is y. G, whose input is y and output is z. And H, whose input, you can always read the input by where it crosses the box. So x is the input and z is the output, so that's this. Okay? In the next dimension, we have alpha, whose input is f. It has 2 inputs, f and g, and its output is h. So alpha goes right here. And then beta, same thing. It has an input of f, and an output of g. So beta, I now have to draw it like this. Beta. And now theta is a cell whose input is alpha and output is beta. So theta is like a 3-dimensional cell filling this in. Okay, so you should think of this picture as these two are on top of each other, and there's 3-dimensional space filling it in. Okay. Okay. So these pictures describe a certain class of pasting diagrams, and what I'm going to try to do is build a logic out of these pasting diagrams. Okay. I'm going to treat them as sort of formulas. Now, let's see. Nope, you like that, huh? Right, right. So why don't I enumerate some of the things that we see? So in dimension 0, there's a unique thing you can do. It looks like this, because it's both linearly nested and a corolla. In dimension 1, there's a unique thing you can do that looks like this. Okay, because the first one has to be linearly nested, and the second one needs to be a corolla. It can only have one input and output. In dimension 2, there become more things you can do. So let me start to draw. So this is dimension 0, dimension 1. So this one, which looks as follows. There's 1 point, and then there's a box, and yeah, so this one looks like this. You see, there's no, if I draw the tree corresponding to a single box, it's just a single line. And this one has no box external to that single line, but there is still a target one-dimensional cell. So this one looks like this. The input is sort of degenerate. Okay, and then you have this one. Let's see. I'm sorry. Yes, like this. So it ends with a corolla, but it has no leaves because there are no boxes right here. Yeah, a tree with just one node. So the ending thing is always going to have to be a tree with just a single node. Did I just make that word up? Okay. I didn't know it was weird. All right. Okay. Right. Then we have this one, which looks like this. And this will look as follows. Okay. X, Y, Z, so X, Y, F, G, alpha. X, Y, F, G, alpha. Okay. And then you have things that, well, we did one over here. You have things that look like this. Yeah. In general, in dimension 2, what you can do is put n boxes right here, and then you have to be done because the next thing is supposed to be a corolla with n leaves. Okay. So if you think about what the condition. Oh, sorry. This will have more boxes like that. You have a certain linearly nested thing, you get a line. You have to put a box around it because the next thing can only be a corolla. And so these look like shapes that have some number of arrows and a single output arrow, look like this. So this is everything in dimension 2. Okay? Yeah. Uh-huh. Yeah. Yes. Okay. So in the picture I'm drawing, that's true. You would need to specify that bijection because you could be symmetric. Right. It's not just the same number. In practice, I think of these in practice when you sort of implement this thing. You're really looking at 2 trees in each picture, but you only need 1. So when you go to implement something like this, the bijection is given to you. But in any case, but yeah, you do need to pick a bijection between the leaves and the one right there. We're always going to be drawing these things labeled, so then it will sort of be clear, I guess. Okay. Okay. Does this make sense? So you can see that this definitely is a more complicated set of shapes, right? The difference is, in dimension 2, when you start drawing these things, you realize that the dimension 2 pasting diagrams you create are intimately connected with what's known as string diagrams, okay, string calculus. So in a sense, you can think of the Opetopes as sort of something like an extension of string diagrams to all dimensions, although that's not, that's a rough sketch of how you should think of it, but that's one way. That's one way you could think of how to do these things. They're somewhere, because they're built from trees, I sort of think of them as they're somewhere in between the geometry of higher categories and sort of ideas from formal languages and logic and things like this. Okay, so this is why I think they're appropriate for what we're doing right here, and I'll show you sort of how you can make that true. Okay, what else do I need to tell you? Oh, okay. So those are the objects. Let me point out a couple things about this setup. So because the last thing always needs to end in a corolla, that means the box before it must consist of just leaves, in other words, the tree, and a single box in behind, right? Because these correspond to the boxes on the tree, and this one corresponds to anything you have in the middle, but because there's only one, there has to be a single box that encloses everything. Okay, does that make sense? So that means that whenever I have, right, so that means they will always end like this. They will always have a corolla and a thing with a box. Now, if I erase the box, this configuration I will call a frame. It's exactly the analog of the boundary of a simplicial set, okay? It's just taking out the single cell at the top. So if you were to do that here, if I erase alpha, I now have a frame. In other words, a place where a cell could go, okay? And similarly here, if I erase the top dimensional cell, I have the boundary of that cell, okay? So you can pick out the boundary by just erasing the top dimensional cell, okay? Second is that if you erase this as well, so that we have just a configuration like this, I will call this a pasting diagram. Because what it is it's a bunch of cells of one dimension lower which have been arranged in a certain configuration, okay? And over here, if I erase the outer cell of this frame right here, what I get is this. And if I erase the outer frame of this cell right here, what I get is a linear pasting diagram, a bunch of one cells glued together, okay? And this shows you diagrammatically that this definition satisfies the sort of main defining characteristic that sort of people often give for motivating the Opetope, which is pasting diagram n minus 1 pasting diagrams of Opetopes are in bijection with n-dimensional Opetopes. Okay? And that bijection you can see right here, because anytime you have a pasting diagram, you can always surround it with a single box, and you can always draw the corolla that corresponds to it. So here's the end cell, and it's in bijection with the n-1 pasting diagram by just this two-step process. Okay. This,
Like erasing the output face in some sense.
yes, exactly. So the frame. So if you're doing simplicial sets, the frame is like the boundary, and the pasting diagram is like the horn.
Except that in same sets,
There are many different horns. Right.
In this case, there's only one.
Yeah, there's a sort of chosen specified horn because the external pasting diagram sort of is the horn. Okay.
And in that diagram down there, it's the bottom single arrow that spans all the arrows.
Yes, exactly. Yeah. Okay. Okay. So far, so good. The next thing is I should tell you what the morphisms are in this category. Well, I'll do it like this. Every box in this picture is a lower dimensional cell. Okay. So we want the morphisms in the category to represent face maps, sub cells of the thing we're looking at, right? So let me put this one back and all. So how do I get a morphism? Well, to find a lower dimensional cell of this thing, all I have to do is point to a box. So I claim, for example, this is a morphism, okay? So the point is, in this cell, there's one down here of dimension 1, and there should be a face map which tells me that this thing maps to something of dimension 1. Does that make sense? Just like if I have the simplex here and I point to a cell, say the back face, I know I should have a map to that two-dimensional face. Okay, that corresponds to whether I do this or not. I'm going to think of the codomain. The face is the codomain. Yeah. Anyway, I'm going to draw this as a face map, and then you can choose whether you want the arrow to go up or down. It doesn't really matter. Yeah.
You chose a box and you put a star on it.
Yep.
This box is
I'm saying this box is a one-dimensional subface of this whole thing. This represents some piece of geometry in dimension 4, and I've pointed to a one-dimensional face of it. So what I want to do is now show you how to find what that one-dimensional, well, I shouldn't have done one-dimensional because all one-dimensional faces look like this. So I can tell you what the codomain will be.
my question was, you could have chosen a box that is not.
I could choose any one. So for example, let me choose this one.
You could choose a box that is not red.
Yes. Every box corresponds to a face. The red boxes correspond to outer faces. So I'll show you what that means in a second. Okay, so let me show you how to compute. So if I point to this one, I want to know what shape is it, what codomain shape is it. Okay, so it's a very just sort of simple. I should use a different color than red because I already used red. And there's just a very simple way of finding out what it looks like. Well, you go like this. So I'm going to color it blue, and I'm going to color all the edges that connect to it blue as well. Okay? And the edges that connect to it correspond, all the lines in this picture are boxes in the picture before. Okay? So this one right here is this box. This one right here is this box. And this one right here is this box. Okay? Agreed? Now, every line which crosses one of the things I just turned blue is a box in the dimension below, so I'm going to highlight it as well. Okay? So this one crosses this one, and it also crosses this one. And this one, well, it touches that one, but it's already done. This one touches this one. And the outer one touches this one as well, but we've already done it. That's okay. And notice this last one didn't ever get touched by a blue box. Okay? So now I'm just gonna draw the boxes that I highlighted. Looks like this. Okay? So I just picked out the subface corresponding to it by watching the crossings, and that means there's a map from this one to this one. Okay? So that's how you can describe the morphism in this category. They just correspond to picking out the drawing the faces. There's one subtlety here which I won't.
So you just redraw the things that you had.
Exactly. Exactly. That's what I'm saying. In this picture, you can see all the faces of the object in question. And to pick them out, you just follow this procedure. You highlight all the lines, and then you just recursively proceed down the picture until you get to the bottom, and then you just pull it out. And that's the target. Okay? Okay. What next?
So you take only morphism face now?
What's that?
You
Yeah. Yeah. So I think typically, well, if you draw it like this, then this needs an op. And if you draw it the other way, it doesn't.
So
There are no I'm sorry. There are no degeneracies.
So that corresponds not delta.
Sure. Sure, but there are no degeneracies in here either, right? So, well, yeah. Okay, does that make sense? Okay. Since we're talking about it, let me just show you. That the globular case is actually a special case. Here's the zero-dimensional blob. So here's the one-dimensional thing. Here's the two-dimensional thing. If I just continue the following sequence, sorry, let me put 0. If I never do anything sort of interesting with the tree structure, and I just continually write boxes closed in boxes, I get this. Okay, so if I just draw sequences of lines like this, you get exactly the category G. So, so there's an inclusion like this, which corresponds to sending an n-dimensional thing here to this pattern repeated n times. Okay, so every opetopic set becomes a globular set by restriction. No, I don't think so. That one, I don't think there's an inclusion. Yeah, so unfortunately not simplicial. Yeah, exactly. No, it actually, they're sort of incompatible somehow. I mean, yeah.
Just a stupid question.
Mm-hmm.
When you start with your sequence of your pile of cards,
Mm-hmm.
can you have an empty pile?
No. No.
So you sort of
Maybe later on, but yeah, later on possibly, but or there is a way to make sense of that. But for right now, I'm just gonna stick with this. Okay. Okay, it's been half an hour. Okay, so maybe let's just let me make a list of things over here that we might come across multiple times, so that you can refer back to them, I guess. So this is my notation for an arrow. Okay, so it's just, in some sense, it's just this is why I think these things are compelling. It's just a direct translation of diagrammatic reasoning into this sort of other picture. Okay, here's going to be here's right. So now for this logic, I'm gonna do something different, which is I'm gonna allow two different kinds of cells, X, Y, Z, and I'll show you, and I'm just gonna distinguish them by color. So the first thing is that I'm gonna draw blue cells that look like this, and a cell that's blue will be called universal. And I'll explain to you what it means to be a universal cell and how to manipulate them. But you should basically think of it as something like an isomorphism or an expression that H is the composite here. So if I do something like this, alpha, this would be my description of a commutative triangle. Okay? It says that F and G and H lie in this configuration, and alpha is a witness that H can be used as a composite of F and G. Okay? So this would be the notation for a commutative triangle. Right. Okay, so what I want to do is give a set of axioms for manipulating these sort of expressions, taking into account the idea of having universal cell, in other words, having composites around. In other words, having these things act like a category. Okay? So let me start to do that. Maybe I'll do it down here. Okay, so another way to say what I'm going to try to do is the following. Oh, I should have just used the other board. Sorry. So let me write set O for this category of functors. Okay, so people would call these opetopic sets. Well, so suppose that we want to make these into opetopic categories. Okay, then there should be a free such thing. Okay, so there should be some sort of left adjoint here from the opetopic sets into opetopic categories, which constructs the free one for you. Okay, and what I'm going to try to do is I'm going to try to give you a description of this functor, and I'm going to describe it as a deductive system. Okay, so we've seen, so in here, if I take a P in here, okay, then P is a functor from this category of sets. So I can evaluate it on any diagram. So what? So this is going to be so ideally some subcategory of this which have enough structure to be. Think of this as like Kohn complexes, and this is like simplicial sets. Okay, the Kohn complexes are the subcategory that we're interested in. And a fibrant replacement takes a Kohn complex, takes an arbitrary one and produces for you something that qualifies as a weak infinity groupoid. Okay? So here I want to consider an arbitrary presheaf and try to describe the free weak thing it generates. Okay? Okay, so if I try to describe the free weak thing here, I need to give you some sort of presheaf. Okay? And so I'm going to say that the value of that presheaf at a particular shape is going to be all deductions that you can make in a certain logic which end in the conclusion that there is a cell of that shape. Okay? So the value of the presheaf will be all valid deductions in a certain logical system which have this shape. Okay? So let me start to sort of set up that system. So incidentally, so I can present at least a finite presheaf by just writing down a sort of set of diagrams like this. Say y, z, g. So suppose I had this list of things, okay? Then what I'm claiming is the value of the presheaf at 0, in other words, the set of objects, is just x and y, because those are the two things of that shape. The value of my presheaf at the arrow is two things, f and g. Okay? So if I want to write some presheaf, I can just give it as sort of a list of pictures. And this list of pictures says that I have an object x, I have an object y, I have a map from x to y, and I have, and z. I should have done that. I put a z here without paying attention. And I have a map from y to z called g. Okay, so if I just write I can just present a presheaf by writing a list of the objects I imagine to be around. Okay, so this says I have an x, a y, and a z, 3 different objects, an arrow between the first two, and an arrow between the second two. Now, what would you expect the consequences of, yeah?
So, a picture like your second one there, X, Y, and F.
Uh-huh.
Would it be reasonable
Yes, yes, yes. I mean, that's how we would do it in type theory. Exactly right. This is sort of F lies in the internal Hom category of X and Y in this category. Yeah, incidentally, the Opetopes have a very similar sort of co-inductive structure, because if you take any frame, I should have said this before, so you have some pasting diagram, and remember you had all Opetopes just end with a corolla. Well, just pretend that this is the start, the base box in dimension 0, and start drawing a linear tree, and then keep going. Do you see what I mean? If I just now erase these lines, what I have right here is I can just continue it with any Opetope I want. Did I just? It doesn't matter. Sorry, this was a side remark that I shouldn't have gone off on. But yeah, there's a sort of similar thing. Every frame has an internal Opetopic set lying inside of it. Just like with globular sets, if you take 2 points, there's a globular set of things between them. For any frame in an Opetopic set, there's an Opetopic set of things between them. Okay, and it's just given by concatenating diagrams together. Maybe this is worth spelling out. Let me just. We got some time. Okay, so suppose that I have this.
Are you saying that the Opetopes themselves can be defined co-inductively?
I'm not totally sure about that. I'm saying they have a similar sort of co-inductive structure in the sense that there's always an internal Opetopic set for any frame. So let me tell you what I mean. Okay, here's a frame, because it would be a corolla, but it's missing its top dimensional cell, right? So there's a frame. So what I'm saying is, so what I can do is, if I want to know this corresponds here to a 2 cell. It looks like this. What are the 2 cells internal to this? Okay, the 2 cells living inside this frame. What I do is I just take this picture and I draw the corolla that would have been there, and now I just copy this. Sorry. You see, I just took this picture and I just concatenated it on right here. So cells of this shape you can think of them as 2-dimensional cells living inside this frame.
Could you draw maybe a sort of classical picture, globular picture of this?
It's just sort of like suspension, right? So I have 2 points. Okay, so that corresponds to this, which is a frame. I want to know what the lines in between here are. So those would be objects of dimension 0. So I just draw an object of dimension 0, and you can see this type is exactly the type of lines right there. If I want to know what are the arrows inside this frame, they should correspond to 2 cells, right? So the arrows inside this frame are 2 cells. So I can get that by just copying this picture right here. And sure enough, those are 2 cells. Does that make sense? There's just a concatenation operation which lifts dimension. It's the analog in the globular category of just shifting by 1. Okay, you might call this opetopic suspension or opetopic looping. You can just concatenate the diagrams. Okay, anyway. Okay, so that's what Mike was saying. You can look at this 2 ways. It's an arrow between X and Y, or it's a 1 cell filling this frame where the frame is X and Y. Okay, it has that same sort of symmetry. Okay, so the point is, if this, I'm going to think of the values of this pre-sheaf. I'm just going to write them something like this. I'm going to think of them as axioms, and I'm going to write down a way to deduce the rest of the things that should exist in this category. Okay?
Should I think of an opetopic category as something in the pasting diagrams all have chosen fillers?
Yes, I mean that's roughly the idea, right? Okay, is that the opetopes are set up so that they parameterize ways that you can compose things and get a well-defined result. Okay, all we need to do is sort of write down a calculus which allows us to produce that result and manipulate it, and hopefully produce the coherent cells as well. So that's what I'm going to try to do. Okay. So I'm going to write down a list of axioms, and then we can play with them. So unfortunately, these have to be a bit schematic because, yeah.
Can you tell how many axioms there are going to be?
5. Oops. But they might look a little ugly at first glance, okay? But you'll see how it works in a bit. Okay, so I'm gonna write it like this. And the first one says this. The dots mean, since the first thing can be nested linearly, so the dots mean you've produced something before, which is a cell, okay? And it could be of any dimension, doesn't matter what dimension, you've produced a cell. Okay, so I should say that the formulas of this logic will be pasting diagrams, okay? So suppose you produce a cell, which can be thought of as just a pasting diagram with a single cell. Then you can produce a pasting diagram one dimension higher with just a single bar, which if you look at it is just, I told you to generate Opetopes, what you do is you draw the tree corresponding to what you've drawn so far. So the tree corresponding to a single cell would be just this, the empty tree with this labeled alpha, if you like. And this I will call empty. So from a cell, you can produce a pasting diagram one dimension higher, the empty pasting diagram. Okay? That's axiom 1. This lets us raise dimension. Well, I'll tell you what the identity is in just a second, but this is going to be a key ingredient in getting the identity, definitely. Okay? I really should have 2 on one board, but I don't know if that's going to work. Okay, so if I've produced a cell, I can generate the empty pasting diagram on the cell of the next dimension. Okay. So the next one says, sorry, suppose, let me see how I wrote this. Let me just go like this, alpha. This need not be x, so let me do x1. And let me use red for this next thing. Shoot. Okay, the dotted things, up there, I draw the last thing solid to mean a single cell. The dotted things are going to mean an arbitrary pasting diagram. So rho I, alpha I. Okay? And so okay. Now, sorry. This may look crazy. It says this. Suppose you deduce that there's some cell, and suppose you deduce a pasting diagram whose target is the input of this one, and I different pasting diagrams, and the target of rho sub I is alpha sub I, then you can glue them together into a new pasting diagram. Okay? Let me show you maybe an example of this would help. So this is a single cell, And these ones, I mean a pasting diagram. So this could have an arbitrary number of cells glued together. Okay? And this could have an arbitrary number of cells glued together. And the target of these things needs to be the input of these.
I'm confused because is this one Opetope all over the line or many Opetopes?
Sorry, it's one here, I inputs, and then I pasting diagrams. That's what these dots are.
Some vertical line?
Yeah.
I don't know, in color or something.
Or you circle around each individual Opetope?
What's that?
Maybe a circle around each Opetope?
Okay. Dot, dot, dot. Okay? A cell with I inputs and I pasting diagrams where the outputs of each pasting diagram match the inputs of this cell produces a new pasting diagram where you've glued these cells together.
You forgot the line coming out of the cell.
Did I? Oh, yeah, sorry. Okay, this just says you can glue sources to targets. This lets you build bigger trees.
Isn't there something to say about how the other part of the diagram gets fit together?
Yes, but I'm not going to say that. It's actually, yes, well, I don't know how to draw it. In practice, it's easy, okay? It's, if you try a couple examples, you'll see that it's totally clear. It can be easily implemented on a computer, say. This is the point of this. There's a very simple, totally clear algorithm for doing this, okay? But let me just give you an example of this thing right here. So I'm going to take, so from my axiom, I can deduce G, obviously, which looks like this. And then I have another axiom, X, or F, sorry, looks like this. So here is the analog of the thing on the left. It's a single cell, okay? I want its input face, which is right here and corresponds to that Y down there, to match the output face of F, which here is this corresponding to this Y down here, okay? Here I'm thinking of syntactic equality of these diagrams. These are good. Everything I build will be totally like comparable syntactically because they're just going to be labels of iterated things, okay? So the input of this corresponds to the output of this. And by consequence, I have the following diagram. Okay? Does that make sense?
Would you mind drawing maybe the same kind of deduction rule, but
Yeah, let's
the
you.
example with classical picture? Just
What do you mean classical picture?
well, arrows and
Let me draw one. Let me draw another one that looks like this.
Why not just this one?
What's that?
Why not just this one?
I don't know. Maybe we want another example. Let me draw it in pictures. Okay. Let me draw one in pictures that looks like this. And you'll see what I mean. Okay. So now F. This rule just encodes the following idea. Let me not spend time labeling all these. Well, okay, fine. Beta, gamma, delta, F, G, H, K, S, T, U. Okay, here's a cell. No, it's totally similar one, but I'm just going to do it geometrically because I think it's easier to see what I'm doing. But the point is this geometric idea just has a translation into these boxes, okay? So this cell, the thing that's on the bottom, goes on the right. The hypothesis is that it has I inputs. Here it has 2 inputs. And the second hypothesis is that you have a sequence of pasting diagrams whose target matches the input. So F matches F, and G matches G. Okay? And the conclusion is that there's a new pasting diagram, which looks like this. Does that make sense? So here's the geometry. A single cell together with a pasting diagram where the targets match produces a new pasting diagram. Yep.
So is it
Yes, that's one way to think of it. Right. It's the analog of substituting into inputs. That's right. I mean, yeah. Okay. So that's what this says. Given a base cell and a bunch of previously created pasting diagrams, you can glue them together when their faces match. Okay. And you can read off when the faces match because you just take the output cell that corresponds to a thing down here. I showed you how to produce faces, so you produce that face, and you ask, is it syntactically equal to the face corresponding to the other one? Okay, this is totally algorithmic. You can just, do you get the same thing or not? Okay. So there we go. So the first rule lets us go up a dimension. The second rule lets us create arbitrary pasting diagrams. Okay, maybe I should go to the other side for the next rule. Okay. The next rule, I guess I would draw it like this. Where's my red chalk? Okay, the hypothesis is you have a pasting diagram. And this is a category. It's supposed to be a category, so what can you do with this pasting diagram? The point is you can compose it, okay? So the... I mean what I said before. I mean something like this. Cells glued together with lacking their frame, okay? A configuration of cells. This rule over here lets me generate them. And then, and so I mean an arbitrary configuration of cells in a tree-like structure. That's what these two rules will generate. Yeah, right, exactly. Okay, and the conclusion is that there's a cell, right, which I would call the composite, filling this pasting diagram. Okay, I mean because this should be the point. These pasting diagrams are parameterizing things that should have composites. So to make this thing free, I'm going to just assert that there's a composite. Okay. And well, the point is, what should you name this composite? And the answer is you only have really one choice. It's free, so its name is whatever the pasting diagram was. Okay? So this is the first instance of a rule where a cell is now not labeled by just a letter. It can now be labeled by a diagram. Okay? And that should make sense. I mean, we're trying to construct or I'm trying to construct the free thing. The free category made out of these things should consist of words in some sense. And what I'm saying is the pasting diagrams are the words. We're just finding a way to write them all down. Okay? Okay, so you have composite. So for example, from here, and whenever you have a composite, what happens is you need to in the next dimension down, the composite needs to live in a frame. You erase all the interior edges. Okay? So again, this is something I can't sort of capture with the rules as I'm writing them, but oh, by the way, and I'm going to add a little circle to note the composite, to think of the composite. So this, I would now write like this. I have a cell between here. I'm going to label it with the pasting diagram and write a composite symbol. And right, so comp. Okay, so this says I had a pasting diagram F and G. And the conclusion is that it has a composite cell right here, which I guess we would write G circle F. And instead, what I'm going to do in higher dimensions, the only way to label that composite is to label it with the pasting diagram that defined it. And so I'll do that and just write a circle, meaning the composition.
There is a system notation for this,
Sure.
I mean, the dots and boxes are a convenient way to imagine it, but when you actually have to start calculating with these things, there's another system of notation, I guess I've seen one, involving tuples and tuples. You can actually find the operations on and calculate with, but you're not
Yeah, I'm not using it.
You're using nuts and bolts.
I prefer this one in a sense. I mean, I mean, the point is somehow to translate the geometry directly into the logic. The terms, the formulas of my logic will tell you what geometric shape they are. If you write out a list of tuples with a bunch of composite operations, right? I mean, the idea is, if we're trying to do higher category theory logically, right? I want to work with diagrams. I want to draw diagrams. I want to do sort of, when we do category theory, we work with diagrams. Yeah.
As I understand it, if you're actually implementing this on a computer, it will be some abstract data structure which isn't just a list of tuples, but at the same time also isn't actual squares and boxes.
It's just a list of trees. That's exactly right. I mean, in some sense, you can think of like, that's why I like this approach, because the terms are not just an abstract syntax tree. They're just a list of trees, but it's not more complicated than that. Internally, yeah, in a certain sense, I think of drawing as these pictures as the internal representation. I'm just working with the trees themselves instead of flattening them out into a line. I mean, somehow it would be incomprehensible if you did that, right? Yeah.
You have an illustration of the use of the composite rule here, but I don't understand perfectly the lines that come out of the internal boxes, the FNG, they are not connected to anything?
Yeah, I mean, intuitively, they're sort of still connected to their outputs right here.
And they are connected to the outputs of the
Yeah,
lower box.
but what I want to do is when I compose them, I'm going to disconnect them a little bit to make sure that this cell still lives on the spine, is how I would have to say it, is external. It actually legitimately represents a cell.
But the term that appears below the bar is a correct fragment of an opetope?
It's a pasting diagram, if you like. I'm not. This thing? I would say this is a derived term in this language. Yeah.
But the disconnected line is part of the information?
Yes, because you need to denote that it's a composite cell. If I didn't disconnect the line, then if I saw it something like this, this is a legitimate pasting diagram, F, G, and K. How do I distinguish between this and the pasting diagram which goes from the composite of F and G to K? And the way I do that is when I take a composite, I sort of disconnect them a little bit so that it becomes a legitimate cell. Yeah?
So am I understanding right that there are two things on control which would kind of look similar to distance, but are different things? You could have a cell where you had two boxes nested inside a bigger box, but
Yeah.
they're actually all part of the same tree at that stage. But then this is different from that. This is just a tree with a single box.
Right.
That happens to be labeled by two boxes.
Right.
That we've drawn inside.
Exactly right. It's named by something else, right, exactly. And in the notation, they would sort of look, they would be identical if I didn't do something to change them. Okay? But intuitively, that's what, yeah, that's right, yeah. Yes, exactly. So this is sort of implementation detail. I mean, I want to really implement this, and I think you could make that clear visually. It's hard to do it with white chalk on a blackboard. Yeah.
The label inside is sort of arbitrary. I mean, it's a convention.
Yes. Yes, that's true. Yeah. That's true. Yeah. I mean, if in practice, when you produce some term like this, you're probably going to want to make a definition. This is my term, term. And you could do that. But since I'm constructing the free thing, what I'm trying to label it by is its composite. You could do, yeah, whatever you like, okay? Yeah. The point is that there should be some new cell corresponding to this. Okay? The next thing is the following. So again, the setup is you have a pasting diagram. And now, so this is the first time we're going to see a different color. The idea is that in between your pasting diagram, okay, you have a pasting diagram. You can draw a box around it. And that composite cell will sit on the box external. So I can draw this like this. Now I need red again. This is a row. So the composite of any pasting diagram will live in the frame opposite from it. And the point is there's now a universal cell connecting them, which I'll draw in blue. Again, we need a name for that cell, so I'll just name it by the pasting diagram again. And this time, instead of a single dot for the composition, I'll draw a solid dot for the sort of filler. Okay? So this now says that if you have a pasting diagram, you can form its composite, and living between the composite, the pasting diagram, and the composite on the other end is what I'll call a universal cell. Okay?
I'm still confused. When you talk about pasting diagram, do you mean what you have called a frame before?
No, a pasting diagram is just a tree of cells. A frame is a tree of cells with one cell behind it, and a cell is just that with a thing one dimension higher.
You said earlier that a pasting diagram was two steps before
Yes.
full stop.
Yes.
So two steps before reaching the end of the corolla.
The frame was like the last word.
Okay, this is,
Frame is a boundary.
yeah.
Pasting diagram.
You mean it's a horn?
Yeah. So,
Combinatorially, there is a projection between
yes,
these pasting diagrams
and the cells of the next dimension.
the frames and the cells.
Right.
Somehow.
They're all the same, right? Yeah, exactly. They're in bijection because I can just erase this one, and now this I would call the frame. I can erase this one, and this I would call the pasting diagram.
I'm very slow.
No, it's fine. So what I'm saying is when you form the composite, that there's going to be a cell, a universal cell filling that interior thing, okay? And so here, this would look like F, G. And then here is the composite. I'm
Don't you have a rule to make these faces?
You can add that rule if you want. So far, I haven't needed it because when you start from the ground up, it's certainly admissible, exactly. If you've produced anything, you had to go by producing the face first. So for what I'm doing right now, you don't need it. And then this one will be universal. And again, I'll name it the same thing. It's going to be it's introduced by the pasting diagram, so it's going to be named by it. But I'm going to put a solid dot instead of an open dot, and it looks like this.
Pasting diagram is one but which has been labeled appropriately with respect to the flea sheet.
Yes, right, right. Yes, yeah. Okay, so that's right.
So, back to the universal rule.
Mm-hmm.
What you drew in the bottom right of the box.
Mm-hmm. This?
Yeah, is the copy of the full Opetopes that you have.
It's this, right? So this composite cell, it will be compatible. It will live. It will.
But you drew something else on the side of it, as if you had taken the full premises, the full.
Yeah. Okay. So yeah.
Is it there or is it not there?
I think technically, I think it should be there. I think you should label it by the entire sequence defining it. In practice, this often never comes up. As Noam was saying, it's kind of arbitrary what you name it. To be totally unambiguous, I think you should name it with the entire sequence. I'm sort of not going to do that because, like I say, as an abbreviation. In practice, you sort of don't need to. Okay. So now Okay, so now the last rule is going to be as follows, and then we'll do some examples if I have some time. So the last rule is obviously the most important. It's like the analog of J, for example. It says, how can you exploit this universal cell that you've produced? Okay, I'm going to write it as follows. Okay, so say you have a universal cell called alpha, and say, so I'll call this Y. Say you have another cell called beta, and that, okay. Okay, so alpha is a universal cell. Since it's a cell, it sits in some frame. That means in the next dimension below, we have some pasting diagram, and we have some target cell. Okay, so it looks something like this. Okay, so the point is, you should think of a universal cell as a rewrite rule, which allows you to change the pasting diagram on top into the cell on the bottom. Okay, so let me call this pasting diagram here rho, and this cell tau. Okay, so I have a universal cell. I can look at the stage 1 before, and what I will see, since it's a cell, I will see a pasting diagram on the outside and a frame on the right, and a cell that's its target. The point is now you look at any other cell where you see the pasting diagram rho on the exterior. Okay, and this could be so in any dimension in between these two. So I'm imagining that I have some beta, and in that beta, somewhere in some dimension lower, I see the pasting diagram corresponding to alpha. Okay, so that's my picture. This thing occurs somewhere. Then there's a new cell with rho replaced by tau. And remember, this is going to sort of participate in some context here. And I'm going to write this as alpha transformed by beta. Okay? Yeah, certainly. We're going to do some examples next. I know. I just wanted to write down all the axioms, okay? Yeah. What's that? Yeah. Yeah. So composition is like completing to a composite. Universal intro is like filling it with a universal cell. This is saying that if you consider all cells in the category which have your pasting diagram on the exterior, there's a bijection between those cells and the cells which have the target on the exterior. So this is why people say with these opetopic models, composition is defined by a universal property. It's saying maps out of the pasting diagram are in bijection with maps out of the single cell. Yes, I'm going to say yes. So let's do an example. Let's do an example, and I think you'll see what I'm getting at. Okay, let's start with some simple examples. I'll just write some axioms, and then we'll just deduce some things from them. Okay, so X is a 0 cell. Okay, so by the empty rule, there's the empty pasting diagram on X. By the composite rule, there's a composite cell for the empty pasting diagram. The composite rule says whenever I produce a pasting diagram, it has a composite. Here's one I've produced. It has a composite. Okay, and what's that? Okay, and actually, when you take the composite here, lower dimensional information has to change, but it's going to look like this. So I'm going to label it as the composite of. Okay, so yeah, there's one thing I forgot to say. This one will be universal, and I have to tell you why. So there's two rules, this one and this one, which I'm going to say preserve universality. Okay? In other words, if every cell in your pasting diagram is universal, its composite will be universal. And similarly, if beta in this thing right here was universal, its transform will be universal. Okay? So the two rules right here are going to preserve universality. So in this case, vacuously, every cell in the empty pasting diagram is universal, so its composite is. Sure, yes. The composite of alpha. That's what we were sort of talking about before, right? I'm trying to name, yeah, if you like. Certainly any system that implemented this would allow you to do this. That's the point. Right, right. There's no, this is the empty one pasting diagram. So when I compose it, I meant cells in the pasting diagram. This has no cells in the one-dimensional pasting diagram.
So the pasting diagram is the whole string.
Yes.
Really. So, but you mean every cell.
The top dimension, yes. We're going to do that next. I just wanted to show you that this is a very simple deduction that says that any cell, and in general, this could have been any cell. Notice this is parametric. Every cell has an identity. Okay? That's the point. The empty rule together with composition gives you the identity. Yes. And similarly, suppose I have some cell here. Let's add another thing to our picture. Here's X. Here's Y. And here's F. Okay? So the point is that by universality, I can replace X with X. The identity map really acts like the identity. Okay? So there is something slightly fishy going on here, but in any case. So the identity transforming F. Okay, so you produce some other one cell between X and Y. Yeah?
Is that correct to think of the universal cells as some kind of definitional equality?
I would say they're like our propositional equality. Okay? So the point is, so universality. Now, there's sort of a problem with the units here, but anyway, this is the point. X, the identity says that any pasting diagram where X appears can be replaced by X, but that's the point. Okay, I mean it's the identity. Okay, so let me let's do a more interesting example. Oh, sorry, that's a bad habit. What do we want to do? Okay, let's suppose. Let's suppose that we assume that we have a universal cell between X and Y. Okay? So I want to show that universal cells act in some sense like isomorphisms. Okay? So here's a deduction that shows that, that this thing has an inverse. So I take the identity on X. And now X is a universal cell, so I can put it over here. And I apply universality. And universality tells me that anywhere I see X, this pasting diagram on the exterior of another cell, and here X appears on the exterior of another cell. It's useful to, by exterior I mean these boxes that I was drawing in red before, the outer faces, I think. This cell tells me that there is a cell with this pasting diagram replaced by this cell. So the conclusion is that there's a cell like this. And it has a name. It's F transforming the identity on X. And in fact, this cell is also universal because I said that this rule preserves universal cells. Okay, so this is my definition of F inverse. Okay, does that make sense? Let's do something more interesting.
Do you mind drawing sort of the classical picture corresponding to these calculations?
Yes. So I have a point. Here I have the point, and I get the identity. And F, the universal cells, are a witness that whenever I have a cell which has its pasting diagram as the target, there exists a cell with this thing transformed by that thing. So F ID X to X.
You might say that, right? F is a morphism from X to Y. And
Yes.
universality says that any morphism out of X factors through F.
That's another way to say it, right? Exactly.
Although you have to do something else to show that they're naturally universal.
Yes, right. And so currently, yeah, so there's a small problem with that, but I know how to fix it now. So I figured I would just present today what I have right now, but I know how to make that work. So you can go through and try to prove that F composed with F inverse is the identity. And the point is, in this language, there's no other way to say F composed with F inverse is the identity, other than to assert that there's a universal cell connecting them. Okay, so this is why it's like propositional equality. The only thing you can say in this language for being equality is there's a universal cell between these two things. So you can go try to produce a universal cell living here, and you'll be able to do that. Actually, you'll fail slightly, but in any case, okay. So
Are you, in your system, are you supposing that you have a procedure for distinguishing universal cells from other cells? Somehow to say that the term is a universal cell.
yeah. So right now, as I've presented it right now, they're distinguished by you can only generate them from certain rules, and they have a different color. Okay. I don't think that actually turns out to be necessary. I think there's a different way to do it, which solves some of these problems with units. But I'll have to leave that for another time. So let me just show you some of the things that you can, for example, do with this. So obviously it gets a bit tedious to keep doing this by hand, but you can make these pictures quite easily. And the point, or what interests me about them, is you can make them easily on a computer. Right? Yeah.
If you start from the premises of the second quality,
Yeah.
you can first somehow compose all the row I,
Yeah.
and then compose them together.
Right.
Or you can first
Right.
compose the big pasting diagram and
Right.
compose this in one place.
Right.
Can you prove that they are equal?
You can generate universal cells that connect those two things. That's the point. Using universality and just applying this universal rule, yes, you can create a big pasting diagram where you show that there's a universal cell connecting those two composites. That's why I call this thing weak, because the calculus generates the cells in question. How do I turn this on?
Delete detail.
probably.
I think we can guess.
Here's a display new. What if we try that? That's good. Okay, so here's the axioms presented sort of in the way I did. So empty, pasting diagram, composition. I called it reflexivity because originally I thought of it that way, but maybe that's not too useful. Here I called it universality intro. And then the universal thing. You can see you have a universal cell with some pasting diagram and a target cell. You see that pasting diagram participating in another cell, and you're entitled to a new cell where the target has been replaced by that cell, and then you need to label the higher dimensional one. So here, as you were asking, like, what should the labels be? Here I've been very expressive. I've actually labeled it with the whole opetope, right? Okay? Yes, this is tedious to do by hand, but a computer can do this easily. I mean, internally, this is not a problem. Okay, so here's a deduction of the horizontal composition of two cells. So here's my setup. Here's a picture. So I have X, Y, and Z are 0 cells, X, Y, and Z. I have F and G from X to Y, Y to Z. You can see I've just copied down the pasting diagram in these terms.
So you talked about an Opetope sequence and you draw them, you drew them horizontally on the blackboard.
Uh-huh.
Here it's the Opetope sequence is on vertically.
These are all just independent. I mean, so this is a bunch of different. This is a picture.
Is there 4?
There's one for every cell in this picture. So 1, 2, 3, 4, 5, 6, 7, 8, 9. My context consists of 9 hypotheses. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I just organized them that way. Right? Okay. So given a pasting diagram like this, I want to show you that there exists a horizontal composite of that pasting diagram. What should that be? It should be a cell between the composition of F and G and the composition of H and K. And here's a deduction of that cell. So how does it go? You start with H and K. You paste them together because they agree. You consider their reflexivity cell. So I can actually draw the pictures that correspond to the different steps here. So our picture looks like this. So we start out with a picture that looks like this. Okay. So at first I'm gonna leave off the top 2 cells, and then what I find out is that by composition there's a cell here, which is the composite, but I'm more interested in the universal cell that connects to it, which is right here. Okay. So I get that cell. Now I take alpha and beta and I paste them, my 2 cells, and I paste them to the outside. Right? So I make this pasting diagram, which looks right here. This is the reflexivity on that cell. Okay? Now I compose that pasting diagram to get a cell which looks like this. A cell in the middle. And now I use the universal property of the composite for F and G to turn that external pasting diagram on F and G into a single cell. It's composite right there. Okay, so now I see, here's a cell that I've produced previously. This down here is what, K circle H, which has the pasting diagram FG externally to it. And so the universal property of its composite says that there exists a cell right here with the composite F circle G. And so, in other words, this term is a name for the horizontal composite of these two cells. Okay? And you can see, and moreover, this proof is like, I mean, it's totally generic in any of these things. If you have any other situation with this configuration of cells, you can simply substitute it into this term right here, and that will be the analogous derivation of the horizontal composite of any other 2 cells. Does that make sense? So these proofs are sort of have this substitutive property, just like proofs of formulas. Okay? What else? Yeah, so here's what I was doing before. I have 2 cells, and I assume there's a universal cell between them. And so here's the derivation I did for you before. This produces a cell that I would call the inverse. And this derivation attempts to show that the inverse composed with F is the identity. And you get a universal cell connecting that composite to the universal property of F applied to itself. And there's good semantic justification in the semantic model that I have that when you apply the universal property of a cell to itself, you should get the identity. In fact, in the semantic model, Mackay sort of defines the reverse. He defines a universal cell as a transform. So there's good reason that should reduce to the identity. But I have a slight variation where you can actually produce a cell between this and the identity, in which case it would be the composite. So yeah.
Can you go back to the previous one for a second?
Sure.
So you said that it was, so the proof is definitely generic in all those things in the context.
Right.
Right. But if you look at the conclusion,
Yeah.
right, it doesn't have like things coming out for all the hypotheses. Right. So is it only generic in the sense that like you can recreate this proof for any like different kind of thing in the context, as opposed to, you know what I'm asking? There's a
Yeah.
sort of internalized sense in which you can substitute.
So that's in a sense what I sort of am working on right now. I would like to say that now I can abstract over one of the cells in these things. Just I would like to do lambda introduction here for a cell, is what you're talking about. Yes. That's what I have in mind eventually. Right now, you need to think about variance and things like that. I think there is a sense in which, yes, you can interpret this proof as a certain cell in a higher category. That's sort of some of the approach, right? That's the idea of doing things this way, is that.
But this category might not have that structure. You might not be able to internalize all these.
Yeah, there's certainly more to think about there. Yes, I agree. For now, this is like Guillaume's calculus in the sense that it lacks products or sums or anything like this to call it sort of a logic. It's just the internal language of a category built from these shapes. Make sense? Yeah.
Is it possible, do you think, maybe you've thought about it, or maybe you haven't thought about it, to give a kind of dependent type theory in which the opetopic shapes would serve as indexing for the next level as a dependent type, so that you could build opetopic types?
Yes.
The way that we build opetopic, the way we build globular types by having a iterated series of dependent types, and we
Yes.
use the globularity figures in
Yes.
an external description of the shape of indexing.
Right. So that's
You have a dependent type theory
that's
for making opetopic types.
that's certainly the goal. Yes. So yes. You can. If I were to add sort of type forming rules to something like this, then yes, the point is you would have a rule that says like this. So.
It might be like that. That's not what I have in mind. What I have in mind is you have a more conventional type theory with types and variables and context, where you'd have to say what it means to be maybe it would be a pacing diagram.
Yeah.
Context. You'd have a dependent type over that, and that would be the type of all fillers for the pacing diagram. And then you push that back into the context to have
So-
the new type.
So.
Higher pacing diagram.
Yes, possibly something like that is possible. I suspect it would look very complicated, and
This is a very uniform inductive structure.
yeah, maybe something that is possible. For me, I'm interested in I like the idea that you should be manipulating diagrams when you're doing category theory, and I want to sort of make that idea precise. Right.
This is type theory definition of Opetopes,
Yeah.
which uses polynomial functors.
Maybe if you wanted to encode something like this in type theory, you could use that. It's not totally clear to me what that would get you, right? Precision. Yeah. I mean, yeah, it's possible something like that could work. If you want to build a more complicated system out of these shapes, which is what I want to do, then once you do that, I think you would run into all the same problems you do, like encoding, I don't know, type theory and type theory. The idea is to have something somehow more general.